Hi, my name is Manmeet, and today I'm going to present my project topic, which is a part of course wireless communications. And my project is based on performance evaluation of OFDM system with Rayleigh, Rician, and AWGN channels. So let's begin. So this is the overview of my presentation. I will begin with evolution of cellular networks, then coming on to the problems, then why there was a need of the OFDM, then different fading environments and noise channels, and then simulations, then finally the summary and conclusions. So the evolution of wireless communication systems. So here we will see how the communication standards has evolved over the years, starting with 1G, where analog communication was used and which was basically used for voice service. The speed was really low, that is 2.4 kbps. Then 2G came, which introduced the concept of digital communications with standards like GSM and CDMA, and speed was increased to 64 kbps. Then 3G, which is most widely used these days, it introduced the concept of multimedia, that is, apart from voice, we could include data, text, and internet things with our system. Then here the speed was 2000 kbps. Then the 4G has recently been introduced, and it is the concept of LT, long term evolutions, and here the speed is around 1000 mbps. So, so what are the problems which are faced by 1G, 2G, and 3G, and why do we need OFDM or the 4G, that is LTE systems? So basically there are two problems: inter-symbol interference and inter-carrier interference. So ISI is a form of distortion of a signal in which one symbol interferes with the subsequent symbols. So now this is unwanted because previous symbols have similar effect as noise onto the present symbol. It is usually caused by multipath propagation. Now coming over to the intercarrier interference. So intercarrier interference is basically similar to ISI, but in the case that since there are in a spectrum there are a lot of carriers, so like intersymbol interference, different carriers can also interfere with each other and cause noise, and that is why we need them to be properly isolated. Now OFDM, which is orthogonal frequency division multiplexing, it is a method of encoding digital data on multiple carrier frequencies. So why do we need this? A large number of closely spaced orthogonal subcarrier signals are used to carry data on several parallel data streams or channels. Each subcarrier is modulated with a conventional modulation scheme, which can be BPSK, binary phase shift keying, QPSK, quadrature phase shift keying, or even QAM, quadrature amplitude modulation, at a low symbol rate. So let's see what's the basic difference between OFDM and FDM. So OFDM is a special case of FDM. Sorry, FDM contains a single carrier, whereas OFDM contains multiple carriers. So it can be better explained by the example of flow of water, which can be explained by this figure here. So in this, let's consider two cases for flow of water. First case, that is the A part, which is this one. Here it can be considered as FDM because there is a single stream of flow of water. And in B part, which is this one, here it is a shower, and here it can be seen as OFDM because here there are a lot of little streams. And if we use a thumb as interferer for both cases, then we can easily see or understand that OFDM will be more efficient against it. Now the interference concept will be clearer from the example of making a shipment via truck. Consider this example here. So the A part can be considered as FDM, where a single big truck is used to carry the shipment, whereas the B part can be considered as OFDM, where a bunch of small trucks, that is 4 trucks, are used to carry the shipment. So let's consider a case. In case a truck met an accident, or interference you may call so. All cargo is suffered when big truck is used for shipment, whereas only one-fourth of it will suffer if we are using OFDM technique. That is, only one-fourth of our cargo will be suffered or it will be destroyed or whatever. So that was a basic difference between OFDM and FDM. Now, now the O, which is standing like in front of OFDM, it's basically orthogonality. So why do we need orthogonality? In OFDM system, the subcarrier frequencies are chosen so that the subcarriers are orthogonal to each other, meaning the crosstalk between the subcarriers is eliminated. This is one of the reasons why we don't face ISI in OFDM. Orthogonality occurs when at the peak of each subcarrier spectrum, the contribution from all other subcarriers is zero. This is what basically makes OFDM much more spectral efficient, and it can be seen from this figure here. When the peak for first subcarrier is present, other subcarriers have zero values. This is basically the simpler version to explain the orthogonality in OFDM. Now we will move on to the OFDM communication block. So the OFDM communication block consists of the transmitter, here this one, and a channel, radio channel model, and finally OFDM receiver. So basically the transmitter consists of a random data generator which generates a random bit sequence as input. Then comes the serial to parallel conversion. Here input data stream is converted into the word size which is then transmitted to the next stage. Now we do need modulation to encode the data. Then comes the inverse Fourier transform, and we usually do inverse fast Fourier transform. So basically the inverse Fourier transform is used to form time waveform from the frequency signal it gets. Then after that, again parallel to serial conversion, then guard band. Now guard band is an important concept in OFDM. Guard band is used to achieve high level of multipath robustness because time for multipath signals from the previous symbol die away before the information from the current signal is gathered. This eliminates ISR. Also, using cyclic prefix as guard interval helps. Cyclic prefix keeps the transmitted signal periodic, and this technique helps avoid ICI, which I talked about, which was the second problem. And the channel. Now coming on to the channel can be modeled to account for different fading environments and noise channels like AWGN. So at the receiver, when we reach the receiver here, so basically it reverses the whole operation from the transmitter side. Now the fading environments and noise channels. Now we have different fading environments and noise channels. I will talk about two fading environments, Rayleigh and Rician, and then a noise channel which is additive white Gaussian noise or AWGN noise channel. So Rayleigh fading. Rayleigh fading is a rational model where transmitted signal is scattered by many objects in the environment before it arrives at the receiver. But here there is no LOS. That is, there is no LOS path existing between the transmitter and receiver. It only has indirect path, and the probability density function of the Rayleigh random variable is given by this equation. Now coming on to the Rician fading, it occurs when there is a LOS as well as the non-LOS path in between transmitter and receiver. That is, the received signal comprises of both the direct and scattered multipath waves. So basically it occurs when one of the paths, typically a line of sight signal, is much stronger than others, and it is modeled using this equation. Now you can see if the rise factor k, which is this one and this one, and if it is 0, then basically Rician faded envelope reduces down to the Rayleigh faded envelope. Now there is a noise channel. We usually use AWGN channel. AWGN is a noise that affects the transmitter signal when it passes through the channel. It contains a uniform continuous frequency spectrum over a particular frequency band. So this is how we can, this is basically the AWN channel capacity. And now coming on to the simulations. I use MATLAB for the simulations, and MATLAB is fairly used these days for different communication systems. And there's a website called MathWorks. You can go there and explore about MATLAB. So basically, I will talk about how Rayleigh and Rician environments behave. So I used MATLAB, and here you can see three figures. The sorry, the first figure explains how a baseband IQ packet without Rayleigh channel looks like. The second one talks about the baseband IQ packet in the presence of Rayleigh channel, and third is a multi-path model for Rayleigh fading environment. So now the Rician behavior. So I simulated Rician behavior as well, and again the first one shows the IQ packet without Rician channel. Then after the introduction of Rayleigh channel, we can see there is a noise and it is being distorted or somehow. And finally the multipath channel for this Rayleigh channel. So simulations of OFDM. So I will now go on to the simulations and I will let you see how I simulated it. So first is a Rayleigh channel as I talked about. So when I run it, this is the figure I get. This is the figure with Rayleigh channel. This is the without Rayleigh channel, and finally the multipath model in the presence of Rayleigh channel. Now we will talk about Rayleigh channel. So when I simulate this one, I again get 3 or 4 graphs. This is with Rayleigh channel, the baseband IQ packet, without, and finally the multipath channel. So now where was I? Okay, so I simulated OFDM in 2 parts. The first part consisted of QPSK modulation with fading environment used was Rayleigh and noise channel was AWGN. The plot consists of signal to noise ratio on x-axis and bit error rate on y-axis. Now we will go to the simulations part. This one. Now if I simulate this one, we will have a lot of curves. I will explain some of them. So this is basically the SNR versus BER plot of QPSK modulation in Rayleigh channel. So this is where we can see the theoretical as well as simulated Rayleigh graph, and this is the AWGN graph. And here we can see there are the constellation values of different SNR values, and if the SNR is increased, basically the constellation becomes more clearer, which is shown in this part. So here we have two values of SNR, 24 and 27. So we can see the constellation is much more clearer with the second graph. Then in part 2 I simulated the OFDM system in BPSK modulation with Rayleigh environment and again AWGN. So I will cover that as well. This is the plot. I will run this one. So this is the plot I was talking about, bit error probability for BPSK in Rayleigh channel. So again, simulated result is very much in correspondence to the theoretical one. So now summary and conclusion. So OFDM has been studied to provide solutions to problems like ISI and ICI. The simulations was covered, which was done in MATLAB. So OFDM has different advantages and is unique, and it is one of the most widely used systems today. And it has a great potential to be a part of 5G communication system, which I believe. Thank you.